Well, good evening. Nice full house here today. I am Dennis Wick, member of the Board of Trustees of the library. Before we begin our program, I'd like to direct you to the library's website for the listing of all the programs, everything from our children's programs to the digital archive to upcoming speakers. Next Tuesday, June 2nd at 5:30, we welcome Northeast Harbor artist Richard Huck as he describes his journey in the process of creating Huck's Ducks, which is a fleet of, this is even better, Huck's Defender decoys, which are on display behind me here. We're recording this event this evening, so you'll see it soon posted on our YouTube site. And for those of you who are on our website, please use the chat feature to ask questions. For those of you who are donors to the library, we want to thank you very much for your support. The library is a nonprofit organization that is free to all. 90% of our revenues for operation comes from annual giving and from our generous donors. To our donors, we thank you. For those of you who are not donors, we would welcome your joining us with this little thing here, which is at the admissions desk. So please come and join us. For 1,000 years, people have come to Mount Desert Island, drawn by the natural beauty of the landscape and the bounty of the natural resources. As you stand on top of Cadillac Mountain or on the shore of Eagle Lake, you witness a complex history on a scale of time that is unfamiliar to us as people. Visitors and residents alike want to know more about the geologic forces that have shaped this island. Standing on top of Cadillac Mountain today, you are at the bottom of the caldera, 10 miles in diameter that reach 2 miles higher than where you're standing. Many millions of years later, you stood at the same place at the bottom of a gigantic ice mass, 5,000 feet above us. As a sailor, I asked the question, why is the water depth in Solmes's Sound at Acadia Mountain 140 feet, whereas at that navigational buoy at the entrance to the sound, only 34 feet? To really understand these stories, Duane and Ruth Braun have hiked across this island repeatedly and have studied the geology. Their book, The Guide to the Geology of Mount Desert Island, Schoodic Peninsula, and Acadia National Park, is a definitive story of that complex geology of this place. Duane earned his PhD from Johns Hopkins as a professor of geosciences at Bloomberg University in Pennsylvania. Ruth had a master's degree of science from Johns Hopkins, was a professor of environmental and physical geology at Bloomberg. Both are well known because of their teaching, both here at the library and through the senior college. Please join me in welcoming Duane and Ruth Braun.
Making sure things are talking to the Zoom folks.
Yeah.
All right. So this will be a rapid run through a billion years of geologic time. And this is a greatly simplified version of the history. A lot of what we're saying is good, but there's a lot of details that we can't get into. And with all science explanations, they are incomplete. There's always more to be learned. So let's get going here. There's MDI, 25 miles above MDI. So first, we're going to bring MDI to where it is today. And secondly, Ruth will put the pieces together on MDI proper, and I'll finish off sculpting the landscape from glaciation. Many of the diagrams are in our book. Okay, first off, plate tectonics, familiar to many. Really the mountain building process on Earth. What you're looking at is a side view of things 480 million years ago. And at that time, MDI is riding on what we call the trailing edge of the Gander terrain. And we're heading for North America. What has just collided with North America is a line of volcanoes. And what you're seeing is very thick continental crust. The continental crust is relatively less dense than the thinner, much denser ocean crust. The continents act like king-size geologic corks that float high on the mantle. The real recycling project going on all the time is the recycling of the ocean floor sediments. And convection and the mantle, circulation in the mantle at centimeters per year is dragging the crustal pieces mostly sideways. And when they are in the collision zone, they do get things put up in mountain ranges. And the creation of new crust is mostly ocean crust being generated, and that is being subducted. It's the ocean crust that really is being recycled most definitely. Main thing to think about, 2 to 20 centimeters a year, an inch, 10 to 15 inches a year of motion of these plates. And with modern military grade GPS, we can measure the movement of the plates year by year. So here's a whole diagram of all the different plate boundaries, but mainly keying in again on the new stuff coming up in the mid-ocean ridges, spreading ridges. There is a global line of these ridges throughout the oceans. And the ocean crust cools and subducts against the continent, like in South America, or against older ocean crusts like the volcanic island change of the Western Pacific. And in the continents, they occasionally start breaking apart, like East Africa is now pulling away from the rest of Africa. The main thing to remember from all this is that to geologists, ocean basins are temporary. They open and close, open and close. Continents break apart and reassemble, break apart and reassemble. The time scale there is at least tens of millions to hundreds of millions of years. So to the geologist, everything is temporary. Okay, let's take a look at this region. The old part of North America we geologists call Laurentia. Typically more than 1 billion year old, those rocks. This red dashed line was the edge of North America 500 million or 500 million years ago. And all these stripes, these are what we like to call terrains that will be accreted to North America during the Paleozoic era. And then the rest of the continental masses will plow in to give us a big supercontinent, and then things will break apart after that, leaving behind a big chunk of Africa down here in Florida and southern Georgia. Years ago, 1950s, oil drilling there, looking at the fossils, they said, this is strange. These are not North American fossils. Correct. They're African fossils. But anyways, let's look more locally. Here's an outline of Maine. There's the old stuff up there in Quebec, New York State. And then 480 million years ago, green stripe here, that is a line of volcanoes that plowed into North America, was subducted against North America, forms the Green Mountains of Vermont, the Berkshires down in Massachusetts, and the westernmost mountains of northwestern Maine. And then at 450 million years ago, we call the Gander Train is attached to North America, which is the rest of Maine, basically. It had a complicated history on the way here, which we won't get into. There are some other it did some splitting and rearranging on the way here. But anyways, this is what it was by the time it arrived here in North America with MDI on its trailing quiet edge, so to speak. When this collided, the mountain building was here, not here. But then at 420 million years ago, the Avalon train comes in and plows into us. And this is when we are in an active collision zone with a line of about 8 volcanoes from Penobscot Bay to Eastport. One of the biggest ones was here on MDI. If you stand on Cadillac today, the horizon is this line, so to speak, of the Avalon terrain. And then 370, the Maguma comes in, Nova Scotia. And then to finish things off, 300 million, the rest of the southern continent of Gondwana plows into us to form the supercontinent of Pangaea. Let's look at this through geologic time. So the total length of geologic time is 4.5 billion. We get the 4.5 billion from meteorites. Okay, the age of meteorites striking when we find the Earth, that's the leftovers from the origin of the solar system. The last 500 million years was split into the Paleozoic and the Mesozoic and Cenozoic. And all these other terms we won't worry about for your purposes. But Gander, us, we were attached to South America at this time, about 700 million years ago. And then about 550 million years ago, an ocean basin opens up and moves us further away from North America. And then we start coming back towards North America, splitting off of South America about 520 million years ago. And 450, that's when we just mentioned on the map, Gander colliding with North America. 420 is 30 million years later. All the activity here when MDI was what we would call a super volcano. Then we get a few more additions, intrusions of other magma, 370 million years ago. And finally, 300 million years ago, the rest of Gondwana, Africa and South America comes colliding in. And just for kicks, we do have evidence of even this collision out in the ducks. The ducks, their material is 300 million years old. So the ducks was an intrusion from this collision. And then 200 million years ago, the Atlantic Ocean starts opening. We're breaking apart Pangaea. And it opens to present time, continuing to widen. And let's finish things off with some global glaciation in the last 2.5 million years. So this is the timing of all things. Let's go back to the paleogeography. Here we are 1 billion years ago with the supercontinent of Rodinia. We geologists now recognize 4 supercontinents going back to 3 billion years ago. And this was the previous one to Pangaea. And so most of the continental masses are together in one place. Q for Quebec, G for Gander, and there's the South Pole. And for 450 million years, basically this whole big mass of continental material will rotate down and become centered on the South Pole. And so we move up 450 million years, there's the South Pole. Big land mass centered on the South Pole. And these arrows represent what's going to happen over the next several hundred million years as Laurentia heads to the northwest and much of the other southern continents just kind of rotate into place. So here we're at 550 million with Rodinia getting broken apart. So a different perspective. So here's Gondwana there, center at the South Pole still. There's the wrench up there. Now, this is supposed to represent outline of Greenland, Hudson's Bay, Quebec. Okay, so get a feeling we're laying on our side, so to speak, and below the equator. Okay, this is the equator at this time. And this is at that period that a line of volcanoes are getting ready to collide with North America. The tectonic terrain. There's Gander just splitting off of the southern continent of Gondwana, the South American part. And Laguna's hanging out over here, and Avalon is, we have a lot of trouble with Avalon to the present day. Maybe different constructions leave it in very different places out here. But anyway. There, that worked. Anyways. So let's move up in time some more, litigation time. We're over here in the Gander terrain position, MDI trailing edge. The line of volcanoes has already collided with North America. And here's Maine yet to be. So during this time frame, we come trucking over to collide with the rest of North America to make Maine. We're perspective here. This is now Gander has accreted, and then Avalon is coming in. And that's when MDI is at the active plate boundary where a collision is occurring, generating the heat, if you like, to produce volcanic action. So note, we're still below the equator. Okay. We're going to be working our way to try to get across the equator during much of the rest of the Paleozoic. So here's the map of MDI, and Ruth will start putting the island together itself.
I don't know, can you hear me without the? You want to try?
Yes.
Okay.
Okay, good.
Yes.
Thank you.
Put that in there?
Yep.
Okay, Duane's taking you through a little bit of geology in geologic time here. Now I'm going to sort of put things together. And here's the basic geological map of MDI. And we're going to take a look at each of these units, the sequence that they occurred in, and what it means. How did it come about doing it? The oldest rock on the island is the Ellsworth Schist, which is found on the western border over here. The second one is the Bar Harbor Formation, which you find in Bar Harbor, especially if you've ever walked along the ocean path there. What you're looking at is the Bar Harbor Formation. We'll talk about that in a minute. And then you have this whole series, starting down here with the Southwest Harbor Granite and the Cadillac Granite, Sonesville Granite, had all kinds of activity. They gave us some various magmas and igneous rocks on the island. So we're going to take a look at this. We put this in the geologic time scale. Duane's already gone over this. The first thing that happens is MDI, the metamorphism of the Ellsworth Schist. We'll talk about that as we talk about the Ellsworth Schist. One thing I want to point out here, Ellsworth Schist is a metamorphic rock. It's been changed by heat or pressure. And that's the only thing we can date. So when we talk about how old the Ellsworth Schist is, we're talking about the age of metamorphism. Now, it had the sediments that were metamorphosed had to have been produced at some point before that. Uplift and erosion, Bar Harbor sediments, about 465. Then all the intrusions that give us MDI, all the volcanic activity. Some later intrusions when, Laguna came in. Uplift and erosion for a long period of time here, glaciation at the very end. So this is a pretty active place early on, and then you have this long period of not much happening except erosion. And you say, well, does erosion do? Okay, maybe an inch a year, but you're talking 480 years. Okay, we can remove a tremendous amount of rock in that time. Okay, let's take a look at the rock units on the island. The Ellsworth schist is found in the northern part of the island and along the western edges. It started out as silt and clay marine sediments, volcanic ash, and anything else that was being deposited as gander plate moved towards the collision. Okay, this material was being eroded off, moving continental masses, and it was metamorphosed about 510 to 500 million years ago. Think about this. This is metamorphosed. It means the sediment had to have been collected before this. So the sediment itself is, you could say it's much older, but the only thing we can date, at least with the present materials that we have, is the date of metamorphosis. Once you metamorphose something, you've opened it up, things have changed, you lose materials, you gain materials, so it doesn't give you the date of the actual sediments to start with. So they were metamorphosed somewhere around 500 to 510 million years ago. The schist was uplifted and eroded. And at this point, I should point out too, we're traveling, okay? We're being moved on the plate. We're not in place yet. We're slowly traveling towards Laurentia. The Bar Harbor Formation is found along the east side of the island. Just keep this in mind. Remember, we saw the Ellsworth schist on the west side. On the east side, we have the Bar Harbor Formation. And you might be saying, well, when you have a volcano in the middle, why don't you have the same units all the way around? Okay, and we're going to find out that it's been tilted. And because it's tilted, we get to see the bottom of the magma chamber and the top of the magma chamber. Side, the top is no longer there. Okay, so if you've ever walked the shore path over in Bar Harbor, you're looking at the Bar Harbor Formation. The Bar Harbor Formation is sand, silt, and marine sediments, some ash. It was deposited somewhere around 465 million years. We don't know exact dates on this. There's no mega fossils that we can date in the Bar Harbor. It'd have to be microfossils, and no one's ever done that work. So we're sort of, I won't say guessing, because we have good reasons for saying it's about 365 million years, or 465 million years ago. But we don't have any direct evidence of that. If you walk along the shore path again, if you look at the units, this is the closest thing we have to a sedimentary rock on the island. It's not truly a sedimentary rock because it's been metamorphosed. It's been changed. It's not the original rock. But it's much closer, and you can see where you have all these different units. Then what's been happening, here's Gander, it's on the North American plate. Now we have Avalon coming in. Avalon is going to collide with Gander, going to create all kinds of energy here in the middle. You're going to have volcanic activity. So Avalon's moving in towards Gander. Here sits MDI right in the collision zone, and this is how we start the Cadillac Mountain intrusive complex. The first thing was the Gabbro intrusion. We'll come back to this in a minute. Southwest Granite and Tremont was the next unit. Cranberry Island series, extrusions of lava and ash. We'll talk a little bit about this too. Then came the Cadillac Mountain granite intrusion. The intrusion of layers of gabbro and diorite into the chamber, and then the shatter zone around the edge of Cadillac Mountain granite. And then last igneous activity that we had is the Soamesville granite intrusion, which was the second largest. So let's take a look at this, what's happening. Okay, the first thing was the gabbro intrusion. We have that left up here in the northern part of the island, a little bit down here in the southern part. And this came from obviously quite deep because it's a basalt. And as it came up through, it's going to follow, what do I want to say? It's going to follow the layering, the units between. Okay, this is what I should have been showing you before. Okay, forgot about that. Okay, here comes the magma. It forms fills. These are horizontal areas. It takes advantage of any fractures or weaknesses. And here you've got the joining between the Ellsworth Schist and the Bar Harbor Formation. So you had a lot of that. And then it went up further and it came out in between the Bar Harbor, some of the Bar Harbor sediments. Gabbro is a dark colored feldspar, another iron rich rock. You can see it several places on the island. One of the best places is at Hall's Cove. You have a big black rock there on the east side of the road that you can take a look at. The next intrusion was the Southwest Harbor Granite and Tremont Felspar site. At one time, what's all that's left is what's left down here in this quadrant. At one time, it had a caldera that we're guessing is about this wide and this large. The Southwest Harbor Granite is a light colored granite, has a lot of quartz and feldspar that predominates. And associated with that now is the Cranberry Island volcanic. Originally, the Cranberry volcanics were considered to be much older than the rest of the island. There didn't seem to be any connection with any of the other stuff that was going on here. So this was originally thought to be a much older activity period. We now know, thanks to dating, GOC in the 90s did geochemical work, and the Cranberry Island series consists of about 10,000 feet of volcanic layers, and they're tilted on edge. They're not normally when a flow comes out of a volcano, it's fairly gentle. Okay, these things are tilted at almost a vertical axis. So something's happened here that was strange, and originally, because of that, they're much lower in the stratigraphic unit, and people thought they were some sort of activity that was prior to all this going on. But we know now that this is the extrusions of the Southwest Harbor Granite. Okay, so the Cranberry Island volcanic rock is a layers of pyroclastic. Pyroclastic means fire pieces. Okay? This is just an example of what we think some of these eruptions would have looked like for Mount Desert. you get large ash clouds. This is the fine material that you see in here. These blast out, it breaks up the bedrock that it's coming through, and you're left with pieces coming down that are very angular. And you can see things like this down at the seawall picnic area. Okay, I like these sort of cartoons. It's a lot easier for people to understand what's going on when you see something like this. Okay, so here comes the Southwest Harbor Granite. It comes in, it must have made a caldera, had a surface flow. This is the Cranberry Island volcanics. So you had an erupting volcano, it deposited the layers out here. You notice they're way up here. And then we had a whole series of later intrusions. Cadillac Mountain Granite, you're all familiar with if you've been on top of Cadillac. It's that nice reddish color. It's a little bit more red than what normally would be thanks to the fire of 47. It heated things up, and whenever you heat rocks up, they have a tendency to change color a little bit. So coming up through, you had the Cadillac Mountain Granite intrusion, formed a caldera. One of the questions was, why did it erupt so violently? We now know that into the bottom of the chamber, we started to have, excuse me, started to have more volcanic activity, and that volcanic activity put energy into the magma chamber. Originally, geologists thought that when you have two magmas come together, you mix them. You got a sort of, you know, something about half and half. We now know that that doesn't happen. Okay, you can't basically mix magmas. Instead, they try to rise up, they try to keep separately. And what we had with the Cadillac Mountain is it came up. Okay, I'm gonna go here. This is much easier. You can tell that I'm not used to talking this much about it. Okay, here's the magma chamber. You had an eruption. The eruption was from this gabbro that was injected into the bottom of the magma chamber. This overheated the magma chamber and caused a catastrophic eruption that blew things out of the material. It broke up the material on top here, and the whole caldera sank down in. So you can't mix magmas, but you can inject them in and have an extra energy that overpressurized it and had a violent eruption. Okay, if you go especially to the west side of the island, which is basically all private property, so most of you have never seen any of this stuff before. When you inject one magma into another, there's not much mixing. Instead, there's what we call magma mingling. And you end up with sort of bars or lines of material that this is the granite. This is the Cadillac Mountain Granite. These are the pieces of basalt that's coming up in, and they'll come up, they'll break into pieces, and they move horizontally. So you end up with sort of layers. And this is always a problem for geologists is, you know, if magmas mix, why should you have something like this? And this doesn't make any sense. But as we manage to do more and more in the lab and get an idea, we realize now that magmas don't mix for the most part. They mingle. Most of you are old enough to remember lava lamps. Right? Lava lamps are a good example of the same thing that's happening in the calderas around here. You're not mixing it, but you're mingling it. There was so much energy put into the bottom of the caldera that you had a catastrophic eruption and you blew off and formed the shatter zone. The volcano basically overpressurized and it fractured the rock around it. And that fractured rock fell into the magma chamber and you get the fracture zone around. And here again, bring the magma in, it overheats the magma chamber. You have a catastrophic eruption. Here's the magma mingling, or the shatter zone. This is at Sand Beach. If you go to Sand Beach and walk clear across the beach to the other end there, you have the, cliff. These are pieces of Bar Harbor within the Cadillac Mountain. If you take a look at some of the bigger pieces, this is a piece of Bar Harbor. And if you look right around the edges, you can see that it was cooked. The mineral is slightly demineralized, slightly remineralized right around the edges. And you get these inclusions that show you that, okay, this is not part of the Bar Harbor. It doesn't belong here, okay? It was a piece that got brought in. Okay, then we had, if you've ever driven up, and most of you have driven up Cadillac Mountain, you'll notice these vertical dikes. And again, that was something that we had to learn as geologists. When we actually started out in school as geologists, we were taught that to have a dike cut another unit, that unit had to be solidified. It had to be solid. Well, guess what? It doesn't have to be. If you drive up Cadillac Mountain, you'll notice these big vertical black dikes. Because they were originally thought to have been in place after this was solid rock, they were much younger than the rest of the units. We now know that it only takes about 50% crystallization of a magma to make it rigid enough that you can bring another unit up through it for the dikes. So the dikes are actually much closer to the eruption or the magma chamber.
Same age.
Same age. Okay. Okay, then the final injection that came in was this Stonesville granite, the medium grain. This is the stuff that's down on Hall Quarry, which they used and shipped all over the United States, actually. Nice pink granite. So into the chamber of Cadillac Mountain, you put the Stonesville, you overpressurize the chamber, you cause a resurgent dome to form. Here's the original crater from the eruption of the Cadillac Mountain. Now, you notice we put a lake in here? Okay, why did we put a lake in there? Water collects. Water collects, and remember, we're still below the equator. Okay, we're not up here, we're in a very wet zone, so there's lots of water available to make a lake, so we put a lake in there. Poetic license or something, artistic license. But there is a resurgent dome, and we can take a look at. Yeah, yes, I'm sorry. That here. There's 4 other calderas in the United States that go back in time. If you take a look at the Ossipee Ring Complex in New Hampshire, that's about 120 million years. 1.2 million years for the Valdez crater, 35 million years for the Emory, and then put over here in California, you have the Long Valley caldera, which is only 0.676 million years. The baby, okay, it's present. we can take a look at that to get an idea of what this might have looked like, 420 million years ago. Well, let's take a look at it. Oops, wrong way. Okay, so Long Valley caldera in California, is basically an uneroded, very, uneroded. If you go to the Emery crater, Valdez crater, 1.2 million, you're starting to erode some of the top part of this magma chamber. The Emery at 35, the Ossipee at 120. Cadillac Mountain is 420. All of this stuff has been removed, okay? We basically removed 2 miles of rock. This is the caldera, the Long Valley caldera in California. This is just putting in about what MDI would look like. Let's take a look at what it looks like. Okay, very steep sided, not necessarily that high, but very steep sided in a very low spot in between. Research and dome over here. This is what MDI could look like right after the eruption. We had other granite eruptions in Northeast Creek, Baker Island, and seawall. Probably when Maguma impinged. Maguma did not impinge on us directly. Okay, we now got Avalon between us. And Maguma rise. And then the Duck Islands out here at 300 is probably on 10 when Gondwana arrives and form Pangea. I'm gonna turn it over to Duane because I'm using my voice.
Yes, you would. All righty, this is the actual map that you can download from the Maine Geologic Survey, or get a paper copy for $10. Huge piece of paper. But this is the map draped over the landscape, so to speak, emphasizing that all the highlands are within the Cadillac Granite. But also interestingly, there's a sizable area of Cadillac Granite that's not particularly high. Why? We don't know. But anyway. And here's a putting together of the top view, the map view, and the side view. This is the actual cross section that comes with the map. This is not a cartoon. This is constructed as best we can. Best interpretation we had. And so there's all these volcanic layers steeply dipping underground. Here's the bottom of the magma chamber. This is the gabbro material underneath the Cadillac. And the shatter zone here. And the thing to think about is that this is actually the bottom of the magma chamber, or the one part of the bottom. This is the side over here that swings around here. The next 420 million years of erosion. Now, after this is a volcano, we continue those collisions, particularly of the rest of Gondwana arriving to form Pangea about 300 million years ago. We're throwing up a mountain range like the present day Himalayas. Okay. And so you got this incredible mountain range, and we're going to erode it down, and we're living in the roots of that mountain range. Simple as that. And so here's back to our cartoon views. So here's the land surface of 420 million years with the caldera. That's long gone, long eroded away. And down here, we had all these volcanic layers off of here that have been dropped down and tilted. And this whole caldera was tilted up so that it's more eroded on the northwest side and less eroded on the southeast side. So you see some more of the shatter zone material. You don't have any shatter zone here because it belongs up here in the sky. And what you're really seeing is Blue Hill Bay, Stone Sound, and Frenchman Bay. So the mountain range was mostly eroded by running water. This is the present day Smokies in the southern Appalachians. And it's a ridge and ravine landscape, V-shaped valleys and V-shaped ridges in between the V-shaped valleys, and no lakes. Okay, a stream cut landscape doesn't have lakes. Unless you have landslides, but that's the point. So the landscape looked kind of like this for tens of hundreds of millions of years, very steep when it was Himalayan-like in the late Paleozoic, moderately sloped in the Mesozoic, and quite gentle by the time we get to the present. And it's kind of a sketch view of MDI prior to glaciation. There's a low mountain range here across what will become the island. And there's a series of ridges going from northeast to southwest, and there are shallow saddles in between the ridges. And that is a drainage divide. Streams drain directly south, like the Somme stream, but other streams drain north. And they drain north and then turn to go out the Union River, turn north and going out the Skilling and Frenchman rivers. And these will all become bays thanks to glacial scour. So we're looking at the landscape 3 or 4 million years ago. Now the glaciers arrive. Let's do a little glacial stuff for a while. Most people aren't familiar with glacial ice. It's always a conveyor belt. It's always moving. Moving from zone accumulation to zone ablation. The word do we use for all 3 ways of getting rid of glacial ice. And of course, iceberg calving was a biggie for MDI. Much of Antarctica today sublimates, goes directly to a vapor. Now, but also has increasing iceberg calving in the Western Arctic sheet. So this ice is always moving, and even as they say, snow is stationary, it's flowing, it's just saying that it's melting away at the same place each year. And the ice is retreating, it's still flowing forward, it's just melting faster than you can supply ice from further up. What's actually going on here, there's both a sliding and an internal flowage of the ice on the rock surface. Sliding on rock, internal slippage of ice crystals by each other. How you figure this out quite readily, one summer you go up and drill a series of holes into the glacier and then come back and see what they look like the next year. You put plastic pipes in the hole so that you can run an inclinometer down here. The bending of the pipe is the internal flow of the glacier, and the distance between the bottom before and the bottom now is the basal slide. For the most part, we're seeing tens to hundreds of meters of motion per year of these glaciers, though occasionally they will surge a mile. And there's a lot of water that accumulates under the glacier. Another thing to note, the upper 150 feet of the ice is brittle, but the way that blow here, that ice is all a kind of a stiff plastic that's always oozing along. So if you ever fall into a crevice, it always gets narrower towards the bottom. Get the shape. Go back to the landscape 25,000 years ago. There's MDI, 200 miles from the edge of the glacier. Last terminus about 25,000 years ago. What made all this glacier in North America? The North American or lower tide glacier is bigger than the Antarctic one. Okay, even when things are colder in Antarctica, we still have the biggest chunk of ice on Earth. And also big chunks, the Baltic glacier covered the Baltic region, and small mass up in Siberia. But the key thing is all that glacial ice lowered sea level. almost 400 feet. Okay, so global sea level is way down because where the seawater goes in the glaciers. So this whole region, which is underneath the ocean today, we call George's Bank, was dry land. Meltwater draining from the ice across great masses of sand and gravel out here and the rest of the way down through here. Then, at this time, there would be 5,000 feet of ice on top of MDI. 8,000 feet on top of up in the Katahdin area, 14,000 feet up in central Canada. Basically, it's just this huge mass of ice, thickest in the center, and it's oozing all the way around towards its periphery. So 25,000 are down here with 5,000 feet of ice here, 200 miles to go to get back to here. At about 20,000, the ice is starting to pull back from the terminus. And by 15,000, 5,000 years to get across the Gulf of Maine. Also, in the bottom of the Gulf of Maine, there's these deep scoured out areas, deep basins. And those are weaker rock that the glacier could more readily erode and give us these great leaps in the Gulf of Maine. There are also what we call Mesozoic basins. They are partially from the splitting of North America, leaving weaker rock in the basins that is more erodible by the glacier. Alrighty, well, good enough there. From other evidence, I spent most of my career in Pennsylvania, where we found evidence with 5 different glacial events going back to 880,000 years ago. So we know 5 glaciers got to Pennsylvania, they sure as heck got to here. All right. So, and we have good evidence out on George's Bank that the last 3 glaciers did terminate against the edge of George's Bank. But anyhow, so what we're seeing on MDI and everywhere here is the deposit erosion or sculpting of the landscape by at least 5 different glaciations, not just one. And the best information we have today is about 30,000 years ago, the ice first came across MDI the last time around. Got down here at 25,000 and back at 15,000 here. So we had 15,000 years of glacial scour across MDI for that one glaciation. Times 5, almost 100,000 years of glacial cover to give us the landscape we presently have. So a little cartoon here of the ice moving along and picking up debris on its base, and so it's sliding and grinding away at the land surface. Got a hill in the way. You're going to be pushing against the north side of the hill, abrading the hill, scouring the hill, and then on the south side, you tend to pull off the fractured rock at a plucking process on the south side. They tend to give you these asymmetric hills like the Beehive, much deeper in the south, gentler in the north. Though the hill has to be somewhat asymmetric to the south to begin with, to give us the accentuation by glaciation. There's a bunch of the ridges here on MDI and elsewhere that have a very gentle southward slope. And the glacier didn't do too much to that. Okay. Yeah, you should have just slid right down that gentle south slope. But anyways, and then we got the valleys being carved out by the glacial flow. And we have a fjord here on Somme Sound, which is what they call the shallower glacial troughs in Sweden. And this looks much like the Swedish coast. This is the Norwegian coast, guys. It's mountains. Okay, those are fjords. Fjords, several thousand feet deep. Mountains rise several thousand feet above. Swedish landscape, 200 feet up, 200 feet down. That's what we got. And people come here from Sweden and say, gee, it's just like home. And another one of these gentle on the north, steeper in the south, but the trouble is, this is a gabbro sheet. And so that's really tough top there. And so, yes, the glacier helped to steepen the south side, but it already was what we call a flat iron before glaciation, a bit steeper to the south. The biggest change here is the valleys. I emphasized before that there was just shallow saddles in the mountains before the glacier arrived. And ice gets funneled in the valleys and progressively funnels in the valley and deeply erodes the valleys versus the mountains. So here we have removed 100, 200 meters of rock in the valleys, where only we have moved maybe 10 meters, yards, if you like, on the tops. We greatly deepen the valley. Also, you get nice glacial polish and striation lines by the ice dragging this stuff over the bedrock. Remember, ice is 1/3 as dense as granite. So 5,000 feet of ice is equal to dumping 1,500 feet of granite on the surface. All right. So that's a fair amount of weight. And then we get some deeper features, a bunch of these crescentic fractures, like up in Sargent Mountain, crescentic gouges, the crescent's the other way, the beehive in this case. And then this is a glacial deposit map, simplified map of the island. And the main thing is there's a lot of almost bare rock on the island, that's the gray. The green is where there's glacial till, which is a mixture of all sizes of material, at least 2 meters, 6 feet thick. Okay, that's it. In some cases, particularly here on Beach Hill, there's a few spots that there's almost 100 feet of the glacial till. And then the little red lines are subtle ridges in the glacial till that mark the retreat of the glacier. Lavender color is marine mud. The glaciers were pumping out all kinds of ground up rock flour, or glacier milk, some people like to call it, and that is settling out rapidly on the sea floor. And these darker brown areas are beach deposits that are above present sea level when the land was pushed down by the weight of the ice. Talk about that more in a moment. We're going to look at the northern part of the island now, around Hadley Point and the bridge onto the island. First thing is a cartoon again, side view of things. We're looking at how the glacier was operating, what we call marine-based glacier. It's in the ocean. And so mostly it's calving off icebergs. What you're seeing is kind of a springtime view of things. During the winter, the ice has advanced, has dozered up some material here during the winter. And melt coming out from underneath is spreading out this marine mud, and icebergs starting to melt, dropping stuff to the bottom. And you can see impact craters in the mud, if you know what to look for, of the blocks of rock coming off the floating icebergs, bergy bits we call them. So, and during the summer, all these things got to split off. This is going to retreat back here. This is 1 year's retreat. This was the last winter's pushback. It retreats. This winter's pushback, going to retreat. And that's what you're seeing in the landscape. This is what is called a LiDAR image, where we happily remove all the vegetation from the data set. And you see all these lines. These are those annual push moraines, moraines. And they're essentially like tree rings. They give us the yearly retreat of the glacier. And go look for them, lots of luck. It's very simple, okay? 500 feet apart, 50 to 100 feet wide, 10 to 15 feet high. So in other words, across the width of this library, you see a few foot around. Okay, and when you're standing amongst a bunch of spruce trees, What do you see? Spruce trees. Anyways, but yeah, this kind of imagery helps us, visualize what's out there in the landscape. Now, the weight of the ice has pressed down the crust. Actually, mantle material is oozing away from us from the weight of all the glacier. And so, as the glacier is retreating back through Maine, the land is still below the sea level at the time, even though the sea level is lower than present. But anyways, the whole interior part of Maine was ocean for a few hundred years, a few thousand years at most. All the way up to Midway, right near the middle of Knocker. And also, a very rapid retreat of the glacier over 1,000 years, going from MDI up to that area. Now, looking at MDI, our hills stuck out still though. But this is a sea level graph or curve of what was going on. Here's time down here. 15,000 years ago is here. That's when the ice was at MDI. And so sea level is about 230, 240 feet above present. What that means is that the ground was pressed that far down below the sea level of that time. And what's going to happen is that we have rebound. The ice is now moved north. You remove the weight, so the crust is rebounding upward. 10 to 15 feet per 100 years. Or your lifetime, if you're a Native American, you would have watched what was the low tide line become the high tide line. You drop one tide cycle in your lifetime. But anyways, very rapidly we drop down the present sea level of about 13,000. Then it just keeps bombing on downward. Why? Because land is rebounding faster than the global sea levels rising from the melting of the glacier. Now, when the glacier is melting past here, we've only melted 10% of the Laurentide Glacier. Okay, so sea level is still way down. But anyway, sea level then finally starts rapidly rising, faster than the rebound. The rebound is slowing, actually, at this time span. And so we're down at 190 feet below present sea level. And there are features out there that tell us that we have beaches at that level out there in the Gulf of Maine. And then we have rapid rise of ocean waters, and then a shelf it levels off for the reason that we continue to argue about at the present time, and then rises up again pretty well. And so this is the global sea level rise. And here, quite slow for the last 4,000 years. So I gone up one tide cycle, 4,000 years. But presently, if we look at the tide gauge at Bar Harbor, the rate that we're going up in the last 30 years, we'll have at least 10 feet of rise. The next 300, probably in the next 100. We'll see how it plays out. Let's burn that oil, Dave. We like to see things melt, huh? Canadians do, right? Because they're very nice otherwise. The sort of thing, think about, folks, on the average for the last million years, much of Canada was covered by ice. The interglacials, like the one we're presently in, are typically only about 10 to 15,000 years long. And on average conditions, last million years, much of Canada is covered by ice. Yeah. And here, map view wise, the dotted areas are present land masses here, shape of MDI. But when sea level was plus 230, we were several smaller islands. And everything below that has a series of beaches as the sea level fell. The land level rose actually out of the sea. But zoom, it went all the way out to here. So there's still between the Cranberries and Schoodic, there's still a little area that has some water in it at that time. Narrow slot there coming up towards Blue Hill Bay. The other interesting thing is when global sea levels here, these are lakes. Freshwater lakes in the bays, because the bays have been scoured out by the glaciers. And they've become freshwater lakes for a period of here just a few hundred years, here just a few hundred years, here for a couple thousand. Yeah, lake in some sound. We do find freshwater peats in the bottom underneath marine mud present time. And that was enough. More than, this is the third version of our book. We redid the book in 2024 and we added Schoodic to it. We didn't have time for the Centennial Park to add Schoodic back in 2016 when we did the first book. Now we finally got Schoodic now. All right, question.
What went through all this did we have vegetation?
Okay, we did not have trees yet when this was a volcano. No. We're 420 million years ago. We're in late Silurian times. There's lichen, there's moss, there's bryophytes, and that's it. Though some of the bryophytes are several meters high, but there are no trees. Yeah, not yet. It's around 350 million years, we start getting the first tree ferns on land, and the way things go. Yep.
The image that you had, which showed where George's Bank is, was George's Bank there all the time, or was that part of the glacial debris?
Well, George's Bank was built up from glacial
Okay,
debris.
so it's.
Every glacier built up higher.
Yeah.
We get another glacier down here, and heck, it may be above sea level, but anyway.
Right, right,
Right, yeah.
okay.
Mhm. Other questions? Yes.
So there's, I know we didn't address Schoodic here, but the dikes at Schoodic that are really obvious coming. Those intrusion dikes from the actual seafloor spreading event, or those older and?
Now that is a few hiccups of basalt being injected into the granite. There, just like here, all those dikes are, the fancy word is teeny contemporaneous with the granite. In other words,
Yeah.
okay, the granite is cooling slightly, enough to be rigid, and these dikes are coming up through it. And I have a sequence of them. I have 5 different relative ages of the dikes over there, depending on how much they intermingle with the granite. They mingle a lot there, the granite is not, only 30% crystalline. And then some of the other ones are very distinct boundaries. That was probably 70% crystalline. But anyways, but the dikes are all just an injection of basalt into the bottom of the granite. But the granite was crystalline enough to crack and let them come up through. Now, one of the dikes, if you walk to the west from the parking lot, pump over some rocks there for a few hundred yards, you'll hit a really nice black dike and all kinds of nice stripes in it. That is actually obsidian. That is very rapidly crystallized. And that is actually chemically equivalent to the granite, but it crystallized so fast it made a glass. And when you make a glass, you tend to get a darker color, volcanic glass. But anyways, just for fun, look for that dike, yes.
We have a question from Tim Carter, geologist online.
Yep.
And asking, I may not have heard it, but the last continental glacier, do you know the rate it receded back to the North Pole? I estimate it was about 1/3 of a mile per year.
It could have retreated that fast in northern Maine, but also we said North Pole again. The glacier is centered on Canada. The North Pole is an ocean. At most have an ice shelf on it. So yeah, the center of the glacier is in northern Canada, spreading in all directions from there. But yes, in its final retreat phases, it could retreat several hundred meters a year. Mhm. Did I answer the question?
Yes.
Okay. Another one back there. No, fine. If you need to leave, take off. We'll answer questions for the next 3 hours. If you want.
Just a little botanical thing,
Yeah.
that is being talked about among botanists. Some theories and some other things, but, all of you know, in the fall, when you see the oak trees and beech trees, and they retain their leaves, and they're the last to fall off. And the reason is because what Duane was saying is, we were in the equator. And this family of trees, was in the equator and has migrated slowly up north. And, if you wanna anthropomorphize it, then the oak and the beech are saying, why should we're not used to dropping our leaves. There's no reason for us to drop our leaves. We were in the equator. And so they're taking on their own sweet time and they're up here now.
Well, but another interesting thing is that deciduous trees really developed mostly in the Cenozoic. And for both cold, warm conditions and wet, dry conditions. Early on, the forests were dominated by tree ferns and such. They're mainly a tropical wet environment. And the trees had to figure out a different way of doing things to be able to expand into these other environments, both colder and drier environments.
Right.
Anything else out there?